All right, welcome to week 9. We're almost done. Keep it up. This week, we're going to talk about graphs, searching algorithms, and MST. Some quick announcements. Project 3 was due yesterday, so make sure that if you haven't done that, use those late days and grind that out. Final exam, still have some time, but around a month from today. It's never too early to start looking over and preparing for that. One thing to note is that it is in person. So make sure that if you really can't make that, that you contact course admin. Are we writing on paper for the final? Yes, the final will be written. Yeah, it's going to be kind of like a throwback to what, 2 years ago? Feels like a long time since we had written exams. Autograders quizzes coming up. AVL autograder is a bit tricky. Give yourself some time to debug that. And yeah, we're almost done. Keep it up. As regards to questions about the format of the final, I think it's still quite up in the air, but you should see a Piazza post discussing everything about it once we get closer. Okay, so this week we're going to talk about graphs, minimum spanning trees, prims, cruscals, and the handwritten. Okay, so some quick terminology on graphs. A graph is just a set of vertices and a set of edges. And you can kind of notate that, such as G being the graph equals the set of V and the set of E, where V is the set of vertices and E is a set of edges. What is an edge defined as? An edge is defined as a pair, where the first element in the pair is one vertex, the second element is another vertex, and it's saying that there is edge between those two vertices. So I think that the notation can be a little intimidating, especially if you're not the best at math like myself. But if you look at the notation, you just break it down into sets and pairs between the edges. It's not too bad. Okay, and then some notation on that. So you could have directed graphs, which means that the edges have a specified direction, or undirected, where you could go either direction. And the edges can have weights, such as distance, cost, capacity. And there's some examples of this below. Here we have a directed graph where we have directions on the edges, undirected, and then edges that have weights, and it's also undirected. Any questions on the types of graphs or notation for a graph? Cool. Okay, some more terminology. So when we're talking about graphs, a simple path is the sequence of edges that lead from one vertex to another. And a vertex cannot repeat. And then going off that definition, a connected graph means that there's a path that exists between any two vertices. So you can go from one vertex to another vertex along a path. And then a cycle is a simple path from one vertex to itself without repeating any of the vertices in the path or the edges. And then you have a dense graph and a sparse graph. Dense graph is when the number of edges is close to the maximum number of edges. And a sparse graph is when there's kind of few edges. And there's not really a direct definition for when something becomes sparse versus dense. But one thing I like to think about is a sparse graph. You can think about the number of edges is roughly similar to the number of vertices, where a dense graph, the number of edges is roughly similar to the number of vertices squared. Because if you think about a graph, the max number of edges would be every vertex is connected to every other vertex. So if you do the math there, if you have n vertices and each one is connected to every other one, n minus 1, this would give you roughly n squared. So dense, edges are roughly vertices squared. If that's not the case, then it's likely sparse. So you could say equal to or less than here. And then when we talk about cost in a weighted graph, the cost is just what's at that edge. And in an unweighted graph, the cost can be assumed to be 1 for a given edge. Any questions on the graph terminology here? All right. Some ways to represent a graph. We can do so with an adjacency list or an adjacency matrix. For the adjacency list, for each vertex, you list out all of the neighboring vertices. That is the vertices that share an edge. You can see that below. For vertex 1, we have a list of 2 and 5. So that means that vertex 1 shares an edge with 2 as well as 5, and we can see that here. Whereas an adjacency matrix is just this Boolean matrix that specifies if an edge exists between two vertices. So once again, if we're looking at 1, if we want to see what it shares an edge with, we look at this Boolean matrix and we see there's a 1 here and a 1 here, which refers to edge 2 and edge 5. So you can say, okay, there must be an edge between 1 and 2 and 1 and 5. And we can also see that in our graph. So, these are two ways that you can represent a graph. In a sparse graph, when there's not that many edges, you might prefer to use an adjacency list. Whereas in a dense graph, when there's a bunch of edges, you might prefer to use a matrix. As far as like memory optimizations. Okay, and that's all we have on terminology and representation. Now let's go through some questions, and you guys are going to tell me whether or not these graphs are sparse or dense. Remember that when we said dense, we said that the number of edges is roughly similar to the number of vertices squared. So here we have a tree with no cycles. Is this sparse or dense? Sparse. Yes, I agree. If you count these edges, it will be not V squared. In fact, it's very similar to V. Okay, next one. Let's imagine the internet is our graph and the vertices are the number of web pages. Let's change this color. And the edges between those vertices are the number of links between web pages. So you can imagine like Wiki, which has a lot of links, but have a lot of edges. Is this sparse or dense? We have an answer for dense. Why dense?
Because each web page can have, hyperlinks to things that also have, it's kind of exponential, the amount of hyperlinks that you can have, that you can reach through one site.
I see what you're saying. So like maybe there's a lot of hyperlinks like indirectly connected.
Yeah.
But in our definition of hyperlink, we're just saying from like this website to the other directly. So I guess like the number of edges isn't whether or not it can be reached. It's just like if you can click a button on that website and get to the other. So in this case, we would say it would be sparse, right? Because, if our definition of hyperlinks is just, you can get there from the other one with like one click or whatever, how many links is a web page going to have? Maybe at most like 4 or 5. How many web pages are there? On the order of probably millions, billions. So this would be sparse. Okay, and then the final one is the vertices are the words in the dictionary, and the edges, such as 2 vertices share an edge if they start with the same letter. So apple and alligator would share an edge because they both start with A, and similarly, apple and angry would share an edge, whereas like dog and apple would not. So do you guys think that this is sparse or dense? And once again, this question is kind of asking, are the number of edges on the order of these squared or not? Oh, perfect. We have 2 answers and they're competing. I love it.
I'm going dense.
Anybody want to explain why they think what they think? So we have one answer saying they think it's sparse because, A wouldn't be connected to B, C, D, E. That's true. A wouldn't be connected to all of those. What's up?
I think if you just look at each letter as its own set, then each letter would be dense, right? Because everything would be connected to everything else. And so like the order of magnitude would kind of be 1/26 times n
Yeah.
whatever n squared is.
Yeah, let's write that down. So let's imagine that V is, okay, so we have V, which is the number of words in the dictionary. So for every word in the dictionary, how many other words, let's say that every word has equal frequency. How many other words is it connected to? It would be something like 1/26 to the V, right? And there might be like a -1 in there because it's not connected to itself, potentially. Everyone agree with that? Every word is connected to V/26 other words. Right. So even though it's kind of small, this is still V²/26. So this is kind of a tricky question, but it would be dense. All right. So that's really it for sparse versus dense. Let's quickly go back and talk about graph traversals. And this is kind of like similar to last week when we talked about tree traversals. So there's multiple ways that you can traverse a graph. You could do a DFS or depth first search, or you could do a BFS or breadth first search. With DFSs, we use stacks or recursion. And the characteristic property is that you visit the children before you visit the siblings. And if you remember from last week, 3 depth first searches that we talked about with trees were in order, post order, and pre-order traversals. And they all use a stack or recursion. Then we also talked about a breadth first search using a queue, which was the level order traversal. And the property of a breadth first search is that you visit all of the sibling nodes before you visit any of the children. And it's also kind of interesting with breadth first searches, when all the edges have the same cost, or rather the path is non-decreasing, a breadth first search will return to you the shortest path. So that can be a pretty cool application. And like we talked about with trees, you can also use these for graphs because graphs are similar to trees. So let's go over two examples of this. Here we have a G, which is our graph, and then we have V. You can imagine this kind of like similar to, these parameters are similar to like a node pointer to the head of a tree. And what we do is we look at our head, our first node, and we mark it as discovered. And this is kind of interesting. We have to mark it as discovered. We didn't have to do this in trees because remember, with trees, it's one directional. You don't have to worry about cycles. But now that we're doing graphs, you could potentially have a cycle. And if you don't do this discovered idea, you would just constantly go in a loop and never finish the algorithm. So we take the first node out and we mark it as discovered or explored. And then we say for each neighbor, and this is a DFS, and you can think of neighbor as like a child when we dealt with trees. For each neighbor, you see if that neighbor is not discovered yet. Because if it's already discovered, you don't want to recurse down that because you'd have an infinite loop. So for each child or each neighbor, you check to see that it's not discovered. And if that's the case, you check to see if it's the desired node that you want. If so, you return that node, else you recurse. And that's essentially applying a DFS to a graph traversal. Over here, if we were to run a DFS on this graph and we label the order that we visit the nodes, it would look something like 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see that like if you're looking at 2, you would visit its child before you visit its siblings. And that's because it's a depth first search. Cool. Any questions on the algorithm for a depth first search and how it applies to graphs and graph traversals? What does return R do? Yeah, so this syntax is kind of complicated, but essentially what this person is trying to do is look for a node and return that node if you find it. So, using recursion, eventually if that node exists, then we will return that node. So we set R to the recursion. If further down the line that node exists, R will be that node. If that node does not exist, you will return none. And that's just kind of a way to like propagate information through the recursive stacks back up to the root, if that makes sense. Isn't that what W does? So W is just the vertex that you're visiting. If it's the goal, you return it. Yeah, that's what W does. So R here will be, if there is an answer, R here will be the W of a node further down the line. But it's just kind of confusing because once you return a node, let's say that you're far down the tree. And this is kind of like thinking about recursion. So we're down here and we say, oh, W equals goal. We want to return that. You can't just say return out W because it still has to propagate up to the first call you made. So what you say is like, yes, here you would return that, but then R, the R for this node would equal the return statement of this node. So if you returned W in that furthest down node, then it would be R in its parent. And then the R in this parent would be the R in its child that was the W in its grandchild. And it kind of propagates up the tree. Does that make sense? Cool. Yeah, recursion is kind of tricky to think about. Okay, so that is the DFS. Now let's talk about, I guess the DFS can be implemented recursively using recursive stack frames, or we can implement it using a stack. And this would be an iterative implementation. So we declare our stack, we mark the first node as discovered, and we add it to our stack. Then we just say, while the stack isn't empty, pop that node look at every one of the neighbors. If the neighbor is not explored yet, if it's the goal, return it. If it's not the goal, mark it as explored and add to the stack. So this is kind of doing a similar process as the last one, just using a stack data structure instead. And if we added, so it's, if we added these nodes to the stack in the same order that we added them in the recursive algorithm, it would actually, we'd visit this one first, but then if we add these nodes to the stack, left to right, then the second one we visit would be here. So it actually looks something like 2, 3, 4, 5, 6, 7, 8, 9. So I guess on an interview, if they ever say, hey, that's cool that you implemented it with recursion, that traversal, try implementing with a stack. Sometimes you have to like think backwards, and the first one you want to visit, you want to add last. And then we can talk about breadth first searches or BFSs. And similar to last week, we would use a queue here. So we mark our queue and we mark our first node that we're at as explored and we add to the queue. Then when we say, while the queue is not empty, you pop that node and you look at all that node's neighbors. If they're not explored yet, you add them to the queue. If they're not explored and they're the goal, you return found. But remember, when you add them to the queue, you also have to mark them as explored because you don't want loops. So over here, if we were going to implement this with a BFS, the order would look something like this. And it's kind of interesting, like when do you want to use a breadth first search over a depth first search? In those cases, there's two things you have to consider. Memory-wise, we might talk about this next week, but memory-wise, depth first searches are typically equal or better. But time-wise, they're both O of n, but time-wise, it depends on where your target is. If your target's really far away, for example, here, this would be really good for a breadth first search because the way that you traverse the tree is you kind of go further away. Whereas if your target is close to the root, say right here, a breadth first search might be better because breadth first searches kind of propagate away from the root and visit one node away every time. So there are applications where like a depth first search versus a breadth first search, one of them will find your target faster than the other, depending on where your target is in relation to the first node you visit. And I think we'll talk about that more next week. Okay, and that is, DFSs and BFSs in relation to graph traversals. Any questions on that before we go on to MSTs? Sweet, let's continue. Okay, so minimum spanning trees. We'll cover what those are, the terminology and definition. And then after, we'll go over two algorithms, Primps and Kruskal's, and talk about how those two algorithms work, because both of those algorithms will find MSTs, given a graph. Okay, so before we talk about minimum spanning trees, let's just go over what a spanning tree is. So you would say that a spanning tree is a subset of a graph that first contains all the vertices in the graph, is connected, and doesn't have cycles. So if this was our graph right here, you can see that there's a cycle right here. If we want to take a spanning tree of that, we would have to remove the cycle, while still maintaining and retaining all of the vertices. And then it's also connected, which means that once again, you can go from one node to every other node following a path. Okay, taking that a step further, a minimum spanning tree is a spanning tree that has the lowest cost. So that would mean that it's a subgraph of the graph, contains all the vertices, is connected, is acyclic, because those are all properties of a spanning tree. And then the final constraint is that it contains all of the edges whose weights have a smaller sum than any other spanning tree. And it's not necessarily smaller, have a equal or smaller sum, because you can have multiple MSTs in a graph. Okay, so going over an example of this, if this was our graph right here, this is not an MST or a spanning tree because it has a cycle. So we can turn that into a spanning tree by removing the cycle and keeping all the vertices. Then we look at this, and this is a spanning tree, but it's not an MST because there's another spanning tree that has a lower cost to connect all of the edges, which would be the one on the bottom right. 25. This would be like what, 33? And this would be 41 or something. Any questions on the definition of a spanning tree or a minimum spanning tree before we go into the algorithms to find these? Question is, why is this different from a connected graph? Well, it is a connected graph, but that's just one of the properties of it. You can have a connected graph that has cycles. Connected just means that you can go from any vertex to any other vertex in the graph, following a path. For example, if we had some triangle like this, oops, we need one more node in there. This would be a connected graph, but it's not acyclic. Cool. Okay, so the first algorithm to find these MSTs is Primps. We say that Primps is a greedy algorithm. You might not know what that means yet because we talk about algorithm families later on. However, greedy just means that you can make like locally optimal decisions based on the limited information you have at a given point. And even making those locally optimal decisions, it turns out to be the globally optimal decision in the end. So this is a greedy approach. And how it works is you kind of separate the vertices into two groups. A group that is in the MST currently, and a group that's not in the MST yet. And what you do is for every iteration of Primps, you find a node that is not in your MST yet, and you find the closest one to a node in your MST. And after you find that closest node that's not in your MST to one that is in your MST, you add it, and then you keep on doing that. One property of Primps is that it's best for dense graphs. And we'll talk about the time complexity there in a bit. So the algorithm that it has step by step is we begin with a random node in the graph and we mark it as part of the MST. Then we iterate through all of the vertices in the graph until they are all in the MST. And for every iteration, every vertex, we're going to find the one that's not in the MST that has the smallest distance to one that is in the MST, and we're going to add it. And once we add it to the MST, there's another step that we have to do and potentially update the vertices distances. Because once you add a node to your MST, you're potentially, the other nodes that are not in the MST might have new distances to the closest node in the MST. So let's go through an example of that. And if it's not as clear now, I think this will clear it up. So before we even start our for loop iteration, we choose a beginning node to start off of. And here our beginning node is V1. We say V node is now part of our MST and has a distance of 0 from 1 in the MST. And stepping back a bit, we have a couple columns here. Our first column just says what the vertex is. The second column is a Boolean of whether or not it's in the MST. Initially, nothing is in the MST. The third column is the distance for how far this vertex is from 1 inside the MST. Initially, the default would be infinity when it's not in the MST yet, and you haven't done any calculations. And then the final column just says, you know, this calculation that you got, where did it come from? What was its parent? And you'll use this information to create the graph and figure out the edges between these nodes. So let's go through an example. Initially, all of these were set to infinity and false. So this was, you know, V1 was initially infinity and false as well. But the first step of the algorithm is choosing, you know, an arbitrary node and setting it to true and setting its distance to 0, which we did here. And what that says is V1 right here in the graph. Let's choose a different color. V1 is now in our MST. Okay. I'm just going to write out the steps real quick. So for all vertices, step 1, add closest, where closest is how far that vertex is from 1 in the MST. And then after you add the closest, update distances. So this is kind of like the steps that will constantly be repeating. Okay, so we added V1, vertex 1 to our MST. Step 1. Step 2 is update the distances. So now that we added this node, we have to look at all the nodes that it's touching and see if the distance is now less than what it was prior. And if so, update it. So for example, V1 is touching V2 and has a distance of 13. We check to see what V2's closest distance to a node in the MST is right now, and it's infinity. So we update that and say, okay, now its closest distance is 13. And where would that come from? Well, it is from vertex 1. Then we look at all the other vertices. The only other one that's touching V1, which we just added, is V4, and that has a distance of 7. 7 is less than infinity, so we update the distance to the nearest node in the MST. And then we say its parent, where it came from, would be 1. And that's all we can do for updating the distances right now. Any questions right now? Everyone following along? Right now, we've just gone through one step of the algorithm. We picked an arbitrary node, set its distance to 0, and then added it to the MST and updated distances for the nodes that are not currently in the MST. Yeah. Okay, so now we're on to step 2. And what we do is we add the closest node that's not in the MST to the MST. So we iterate through all the nodes. And if this is false, KV is false, meaning it's not in the MST yet, we find the one that's false and has the lowest distance. That is going to give us V4, right? Because V4 is distance of 7, which is the lowest one among 7 and 13. So now we add it to our MST. So we set it to true. And essentially what this is doing, because we kept track of the parent, we're adding it, and we know that the edge is right here because its parent says V1. Okay, and now that we just did step 1, we added the closest node. Now we update the distances. So we iterate through this list again, and we say, okay, so V4 is not touching V2, so we can't update that distance. It is touching V3 with a distance of 6. 6 is less than infinity, so we're going to set that to 6, and we're going to say V4. V4 is also touching V5 with a distance of 4. That's less than infinity. And it's also shares an edge with V6, which has a distance of 2. And its parent is 4. Cool. So we updated all of those. And now we're on to the next iteration of the loop. So we're going to do that in green. And now we iterate through, we find the node that is closest to a node in the MST and is currently not in the MST. That's going to give us V6, right? Because this is false and this is 2. So now we add V6 to our MST. And the parent of V6, where we came from, was V4. So we know the edge was right here. And now we update distances. V6 is not touching any other nodes, so we really can't update anything here. So then the next iteration, we iterate through the nodes that are not in, that we want to put in, find the closest one, that gives us V5. So we set that to true, throw that in, came from V4, and now we update distances. So V2 is connected to V5 with a distance of 5 right here. 5 is less than 13. So we change that to 5, and we change the parent from 1 to 5. Now we look at V3. V3 is not connected to V5, so we can't update that distance. Next iteration, we go through the list. We see that V2 has a distance of 5, so we add that. Its parent says it came from 5. Okay. V2 is also connected to V3, so we look at its distance and we say, okay, is 16 less than 6? It's not, so we can't do anything there. Then finally, we're on our last iteration. The only node that's left is V3. We add that. Its parent is V4, so we add it there. Now, all of these are set to true, so we're done. And if you look at all these edges that we just color-coded, that would form our MST here. And you can kind of see that this is a greedy approach, because when we're adding a node to the MST, we're making locally optimal decisions. You know, what is the closest node at this point? Okay, add it, update. What is the closest node at this point? Okay, add it, update. And this happens to give us the optimal decision. Any questions on this?
Can you go back one slide?
Sure thing. And this is just color-coded, representing each iteration of this for loop that we're taking. Okay, so this is Primps, which is one of the algorithms to find an MST. Let's talk about the complexity. So if you implement Primps using an adjacency matrix, you're going to get a complexity of O of V squared. And you can kind of see that, you know, going through what we did here, because the for loop is going to run in V time. Within that for loop, we add the closest and update distances. Those are probably 2 for loops that iterate through V sequentially. So it's going to be V times V, V squared. You can also implement Primps 2 different ways. You can use a binary heap with an adjacency list, or you can use a Fibonacci heap with an adjacency list. These are going to change the complexities, but not necessarily for the better. You know, the complexity of using the adjacency matrix is not dependent on the number of edges at all, purely the number of vertices, whereas these adjacencies are dependent. These implementations are dependent on edges as well. So, you know, going back to talking about dense graphs, where there's a ton of edges, the implementation that doesn't have to worry about that is optimal for dense graphs. Like the adjacency list, for example, let's think about if we did have a dense graph. What does dense mean? That means the number of edges is roughly equal to v squared. So this complexity would rather be O of v squared log v, right? If we do substitution, and if you look at that complexity, that's worse than our adjacency matrix implementation. On project 4, you're going to have to calculate an MST. When you do so, ask yourself, is the graph that I'm calculating a dense graph? If it is, you're going to want to use Primps. Let's talk about if it's not. So Kruskal's algorithm is also a greedy approach. And it's very, very elegant and simple, which I like. And you can kind of conceptualize this as like you have a forest of groups of nodes that are in like these little sub MSTs, and you slowly connect them until you get a large MST. And the way that you do that is just iterate. You sort by the number of edges, and you look at all these edges and you say, hey, can I add this edge? Will it make a cycle if I add it to my MST? If not, you add it. So let's look at that. Here we have a graph with a bunch of edges. And let's imagine that we have this list sorted. So now we're going to say, okay, the first, the smallest edge is right here. If I add an edge right here between V6 and V4, will that create a cycle? It won't, right? Because our MST is only these two nodes right now. So then we add it. And then we check the next smallest, which would be right here. Will this edge create a cycle? No, so we add it. Then here, will this create a cycle? No, so we add it. And you can kind of see that we have like two disjoint sets right now. And we're going to keep on doing this until we get one set. So we're at 5. The next one is 6. Will a edge right here create a cycle? No. So we add that. Then we're at 7. And we say, okay, if we put an edge right here, will that create a cycle? It will create a cycle. So we don't add that to our MST. So we skip it and we go to the next one. In this case, the next one is 13. That doesn't create a cycle, so we add it. And then if you look at our graph right now, we have an MST. We could try to look at 15 as well, but if we added that, we would also have a cycle right here. So it's pretty elegant, straightforward. That's that. Any questions on Kruskal's? I think it's a bit easier to conceptualize than Primps. Let's talk about the complexity of Kruskal's. If you think about it, the first thing we do in this algorithm is we sort the edges. And that actually happens to be the bottleneck of the algorithm. So sorting the edges is E log E, where E is the number of edges. Once we do that, we have to keep track of these disjoint subsets. What's a good way to do that? Remember, earlier in the semester when we talked about union find, this would be a good application of that, where the ultimate representative is the set that it's in. And when you're taking two nodes and you're wondering if it will create a cycle if you put them together, essentially what you're doing is you're looking at those two nodes' ultimate representatives. And you're saying, hey, are these different? If so, union them. So for each node, what you'd be doing is 2 finds and potentially 1 union. These are very quick operations, essentially constant. So the time complexity of Kruskal's is E log E, determined by the sorting initially. So you could say E log E or E log V. And the reason why either one works here is because if you think about the number of edges in a graph, the number of edges is always going to be less than or equal to the number of vertices squared, right? because at most every vertex can only be touching every other vertex. So if that's the case, when we have, when we have O of E log E, if we substituted this E right here for V squared, because every edge can only be at most V squared, or the number of edges can only be at most V squared, we can do the substitution because, you know, big O is an upper bound. At this point, since we have an exponent inside the log, from log rules, we can take that exponent out, and this is big O of E log V. So these complexities are essentially the same. So we just said that Kruskals has a complexity of E log V, and Primps has a complexity of V squared. Kruskals depends on edges, Primps does not. When the edges are little, there's not many edges, such as a sparse graph, you'd want to use Kruskals. When you have a dense graph with a lot of edges, you want to use Primps. You might ask now, well, you know, Primps, there's 3 different implementations I can use of Primps. These 2 implementations right here are no better than Kruskals. They're actually the same complexity. We have E log V. And E log V is the same as E log V here. So Primps and Kruskals, Primps with a binary heap, and Kruskals have the same complexity, but in practice, Kruskals is faster. So long story short, dense graph, use Primps with a matrix, V squared. Sparse graph, use Kruskals. Any questions on the time complexities of Primps or Kruskals? And just once again, something like that. Okay. Moving on to the final part of lab, talking about modifying an MST. So we're going to give you 4 conditions of changes that you're making in an MST. And you guys are going to answer whether or not this change could change the MST. And if it could change the MST, how would you find the new MST? So the first condition is, let's say that there's an edge in the MST and we're decreasing its weight. So in this example, we're looking at this edge that has a weight of 8, and we change that to 3. Can this change the MST? And if so, how do we find the new one? It's raining really hard. So in this condition, the edge that we're changing, the edge that we're decreasing its weight was already in the MST. Yeah, you just leave it, right? Because an MST is the minimum spanning tree. It's the spanning tree that contains all of the least weight edges, right? So if we take an edge that's already in our MST and we say, we're going to make it better, that's not going to change our MST. So in this case, can this change the MST? No, we don't have to find a new one. Cool. Okay, condition number 2. Now let's say that we have an edge that's not in the MST and we're decreasing its weight. So here we had our MST, then we said this edge right here that's not in it, let's change its weight from 9 to 1. Can this change our MST? And if so, how do we find a new one? I guess the first question, can this change our MST? Okay, we have an answer that it can change the MST because going through this new edge might be better than going through an old one. I agree. How would we find the new MST now? And I think another student already answered this. So in this case, all we have to do is add this edge to our MST. Throw it in right here. Obviously, adding an edge to an already existing MST is going to create a cycle. So at this point, we look at this cycle and we remove the node, or the edge rather, that has the largest weight. So once we add it, we look at these 3 weights and would remove this one because it has the highest weight. And then that would preserve the MST and it would still be an MST. How would you do this? You could do some type of like a breadth first search or a depth first search, identify the cycle, and then look at all the weights in the cycle. Yeah. Okay. Condition 3. So let's say that we don't have an edge in the MST and we increase its weight. So here, this edge was not in our MST and we changed its weight from 5 to 7. Can this change the MST? Yeah, yep, it wouldn't matter. We already had our MST. If you increase the weight of an edge that's not in our MST prior, that won't affect our MST. We still have our MST. So this cannot change the MST, and we don't have to worry about finding a new one. Finally, you have an edge in the MST and you increase its weight. So here, this edge is in our MST, and we say that we're going to change its weight from 8 to 11. Question 1, can it change it? Yes, I agree with that. Question 2, how can we find the new MST? Any ideas? Bit tricky. So find all the cycles that would include the edge. Yeah, that might work. But we can that might work, but we can simplify that a bit. We already did all the work for all of these other edges, right? We already calculated all those. So we don't have to worry about them. If we just removed this edge, then we have two disjoint sets, right? So from that point, once we have these two disjoint sets, we just look at all the edges that would connect these sets. We have a 9 here, 9 here, 9 here, 11, 9, 9. And we just figure out which one is the least, the smallest weight, and then making an edge right there would give us an MST. So you can see this in this graph. Once we remove that edge, then any of these edges, since they're all 9, would give us an MST. And I think that your solution would also work. I just think that would take a little more work. How could you figure this out? Well, you could build a hash map. And what would you do for this hash map? You could have the key be like the vertex, value be the vertex's component or something like that, like the ultimate representative. Once you have that, once you can know what their ultimate representative is for each vertex in O of one time, then you would just iterate through all the edges and you say, okay, if an edge between these two vertices would give us one complete component, then look at its cost, see how much that costs, and then figure out which one costs the least and take that one. You could do this in O of E time because you just have to iterate through all the edges. Okay, and that is lab. Quickly, let's just talk about the handwritten problem for next week. So given an undirected connected graph in the form of an adjacency list right here, you have to determine whether or not this graph contains a cycle. So this involves doing a graph traversal and figuring out whether or not you have a cycle. And I guess what I would think about in this case is like when you had tree traversals, you never had cycles. So what sets graphs apart? And then how could you determine whether or not you have a cycle? Okay, and that's lab, guys. Thanks for coming. I hope everyone has a good week. And we're almost done. Hold strong.